again. I'm really excited to be here talking about the incredible science that James Webb Space Telescope is delivering to us. And this is my initial slide. It's a beautiful recent image of the galactic center region where you can see all this blue sort of structure that is like hash. It is ionized gas. It's gas that is really getting excited because of radiation around. So this slide is just like a snapshot of many, again, beautiful images. And this is just to give you the sense that there is a lot of Webb data. And when I say a lot, we have about 700 scientific papers based on Webb's data that have been published, which means that it's really hard to give a summary that is fair and includes everyone. So I cannot talk about everything. I wish I could. So what we're going to talk about today, we are going to very briefly talk about what is Webb. And I know many of you are experts because I know there was a series and many of you are acquainted with all this, but we're going to briefly define what is Webb, how well does it work? And for that, we're going to mention the image quality and the sensitivity. And then we're going to talk about a special selection of the transformative science Webb is producing. And I hope you will enjoy it. I was told that I don't have to shy away from scientific plots, so I have, I think, a nice combination between beautiful imagery and some science plots, and I will make sure to define them properly. Before we continue, although I see many of you or all of you know about this, but Baltimore is the home of the Webb Telescope Science Operations Center. So from Baltimore is from where all the commanding is done, all the planning of the scientific observations, everything related to the telescope is commanded from Baltimore, and we use a series of antennas throughout the world. It's a deep space network. There is one in California, one in Spain, and one in Australia. So they are used to download the data and uplink commands to the telescope. So I think it's a Baltimore pride, honestly, to be operating this and to be so heavily involved with this great observatory. So without further ado, what is Webb? Webb is, in few words, is a very large infrared optimized space telescope. And here to your right, you see an animation of the deployment phase of the telescope shortly after it was launched. We're not going to cover any of that, but if you have questions, we can talk about that later, and I'll be able to answer, hopefully, any question you may have. To the left, there is a comparison of the Webb telescope and two other very famous telescopes, the Hubble Space Telescope and the Spitzer Space Telescope. So the first thing you can see clearly is that the mirror is much larger. It is 6.5 meters versus 2.5 and less than 1 meter. So that means that when a mirror is that large, you can actually see lots of detail from your astronomical objects. So you have a lot of detail, and also you have a lot of sensitivity. You can detect very faint objects. It is infrared, which means that we can observe very far away galaxies from the very first galaxies that were obtained, and we can also pierce through the dust, and we can see really cold objects, like, for instance, planets. So there is a series of significant advantages to use an infrared telescope, and in this case, to use one that is this big. I wanted to briefly mention one thing because often, people have said that Webb is a successor of Hubble, etc. So this is an image release that was put out yesterday, I believe, by our colleagues in OPPO in the outreach section at the Space Telescope. And it's a really beautiful demonstration that Webb and Hubble, they are not, they are anything. It's a complementary set of data. Webb observes in the infrared, so that's the orangey structure. And as you can see, you really see all these tendrils and dust surrounding stars and really baby stars being formed. And the more grayish part is the part of the visible provided by Hubble. So you really look at different things, and you're really seeing different types of stars, different types of mechanisms, and it's very, very complementary. And that's the last thing I'll say about it, because you're going to see that in general, there are already many scientific investigations based on data from the two telescopes. Okay, so Webb is a very big mirror, and not only is big, but it is also segmented. This is to the top right, you have a picture, and I just put that because I do like it very much, and it really gives you a sense of how big it is. That's an engineer in a crane, and it's really astonishingly large and beautiful. So the image here, it's one of the first images we obtained was the telescope was deployed and the instruments were starting to switch on. And as you can see in the labels, we do have, this was observation of a single star. And we see 18 stars, kind of blurry, and really they don't look really good. And that means that from each of the individual segments, we were receiving light from the star, and because they were not perfectly aligned and they were kind of, not in the ideal position, because of course it was launch, so launch has many vibrations, and it was not like in a perfect configuration to work as a single mirror. This is what we got. So slowly, our engineers, they were moving the mirrors, comparing, and really figuring out which of these stars corresponded to which segment. So after a lot of fine-tuning, this is what they got. They actually were able to align all the individual stars in the configuration of the 18 mirrors to finally, after lots of really detailed work, this is what we got. So how well does Webb work in terms of image quality? In terms of image quality, it is really astonishing. It is much better than we expected it to be. To give you a sense for those who are into those numbers, 93% of the time, the wavefront sensing, that is how well aligned the mirrors are, it is less than 70 nanometers differences. So our requirement is about 150. So you can imagine that it's really well below requirements and really provides this. And not only we have this perfect star in the center, but if you see the background, all these little dots, they're all galaxies. And this was a really short image. So from the get-go, we really knew that we had a beautiful instrument in our hands. Webb is an open design. Telescope like Hubble and Spitzer, they did have it, well, Hubble is still there, but Spitzer is not there anymore. The design included a tube, and the tube protected the mirror. Webb is an open design, and that means that sometimes it receives hits from micrometeoroids, and you can think of micrometeoroids as like really tiny dust particles that are leftovers from comets and things like that. And we knew this would happen from before we launched, and we receive about 2.5 hits per month, and no, per week. And here, what you can see, I think this was, when was it? May, June 2022, we're receiving one of the segments, either a slightly larger impact or a slightly faster one. And so that little brightening section up there means that that mirror had a little bit of a dent or a deformation. So that was corrected, and we received some of these, but really never had a very significant impact on the quality of the image, as you can see. What we're doing now is we are operationally, so we are observing in a way that prevents many of these impacts to have, because we want to preserve the mirror for as many years as possible. Okay, sensitivity, that is how well we can observe faint objects. That is what we want to see. So to your left, you have imaging. And without worrying about the plots, each of these lines represents one telescope. You have Hubble, you have Spitzer, you have Gemini. Gemini is a ground-based telescope. And you do have, for all the images that are on board of Webb, and you can see that they are all below the other lines. That means that they can observe much fainter objects. And the same happens with spectroscopy. Again, I know many of you are familiar, but the spectroscopy is a technique that it allows you to decompose the light into its individual elements, so to say. So it creates a rainbow, it decomposes all the colors. And with Webb, we do a lot of spectroscopy. So again, here you can see how all these NIRSpec, NIRISS, NIRCam, all the lines that are at the bottom of the plot, these are all the instruments and modes on Webb, and they are all of superior sensitivity than previous telescopes and ground-based observatories. This was the performance shortly before launch. Now we have, at the very long wavelength of the MIRI imager and spectroscopy, we have a little bit of a less sensitivity, but still it's doing incredible science. So to answer the question, how well is Webb working? It's working beautifully. And what we see here, I'm sorry, I just want to move a little bit the banner on top because I don't see, there you are. Okay, so Webb, thanks to this combination of beautiful imagery and incredible sensitivity, it allows us to do previously impossible measurements. And this is a combination of these capabilities. So on the top part, you do have a spectra. And I'm putting several spectra on this talk because about 70% of the time Webb does text data, it does a spectroscopy. And at the bottom, and this image we have on top with spectroscopy, that is the spectra of a galaxy. And I put here on purpose just to introduce the concept of, to the left, you have this sort of very faint emission, and then there is a drop there that is called Lyman alpha. So that drop, that sort of cliff at the beginning, it is a cliff that all galaxies have. That's called the Lyman alpha break. And it simply happens in all galaxies because beyond that, the radiation doesn't, the energy of the galaxy doesn't go out. So if you measure that drop, you're very sure about where in the universe the galaxy lives and how far away, et cetera, et cetera. So it's a very, very important characterization. It's like a fingerprint. If you see that fingerprint, you're gonna know how old the galaxy is and what are their characteristics with all the other information. At the bottom, you see, and this is something that, this is a galaxy that lived a few 100 million years after the Big Bang. So it's really old. And the detail we see, it's really incredible. At the bottom, you see a comparison of 3 different missions, WISE, Spitzer, and Webb. And I think this image speaks by itself. The resolution, the quality is almost as if you can touch it. And also the very many faint stars we can see. So this is a perfect demonstration of how the gains in sensitivity are the gains in resolution. Okay. So before we start talking about scientific results, I wanted to introduce a concept that it's an interesting concept because it goes into the core of what these big telescopes do. So first of all, light takes time to travel. If the light from the sun takes a few minutes to get to the Earth, the light from, I don't know, a lantern, it takes a little bit of time to travel to its destination. Your reflection in the mirror takes a fraction of a second to actually travel. So light is a wave and it takes time to travel. At the same time, the universe is expanding. And since the Big Bang, the universe is just expanding in itself. And it doesn't mean that the objects in the universe are growing. It means that the space between the objects is actually growing. And in that process, the light travels, and light is a wave. So if you imagine like a slinky that you stretch, that's what happened to the lights. And it means that the light moves from the visible to the infrared. So this means that for detecting and for observing those very old, very first galaxies that we know they exist, you need to use an infrared telescope, which is exactly why we have Webb. And just as a little footnote, a reminder that the universe is about 13.7 billion years old. So it is very old, and we're going to talk about really old objects and really new objects. We're going to have like a tour throughout the universe with Webb. Okay, so here on top, you have like a collection of Webb data, starting from the solar system and going to the oldest galaxies we have measured and everything in between. So again, the capability of this telescope allows us to observe everything from Mars until the very first galaxies. Again, if you're interested about why Mars and beyond, we can talk about the orbit, etc. later. But let's start talking about the solar system. And this is the type of quality and the type of data that Webb is delivering. So this is Jupiter. It's beautiful imagery. And the first thing that at least it captures my attention, apart from the clouds, of course, and the atmosphere, is that really you see this very bright planet next to incredibly faint rings and very little moons that are around. So this is what we call contrast. Webb has the capability of measuring really faint and really bright things. And in the planet, the detail we can see, it is just astonishing. And the beauty about studying solar system objects is that they're really close. So we can see the detail, we can see the clouds, we can see the atmosphere, we can see the very famous storm that has been raging for the big red or white spot, I should say here. That storm that has been raging for centuries. And again, if we go back to this planet in months or years from now, we will see that it has changed because it is actually a dynamic. It's like Earth. The atmosphere moves, the clouds move. So these studies do provide very deep knowledge of the conditions of this planet. Another one is Uranus, beautiful. This is a recent image. And here you can see not only the rings with exquisite detail on one of the poles, but you see these very tiny moons that are surrounding it. And it's really never seen before with this detail on the infrared. It's really something very special. So we're going to highlight two very nice science results. And I want to say that all these animations and beautiful depictions are again produced at Space Telescope. This is Saturn and this is Enceladus. And Enceladus is a moon that rotates around Saturn, and it moves in a ring that is farther away and that is made out of water. And let me just play this again. Yeah. So what Webb has measured in incredible detail and exquisite sensitivity is that we knew there were materials, plumes of material coming out of Enceladus. This is actually data. And with Webb, we can measure that was water. There's a lot of water inside. The water is coming from oceans under the crusty surface. This was initially seen by the Cassini mission. And there were questions about what is it? Is it water? Is it water with, I don't know, some carbonaceous? Is it water with CO2? And it turns out that it is only water. So the moon is filling up its own ring with water as it rotates around the planet. Another very interesting result is in Europa. Europa is another moon, this in this case from Jupiter. And what this team has discovered is that there is carbon dioxide over what they call a chaos terrain, which is a terrain kind of, in my head, I depict it as a very abrupt. And in that same terrain, with the Hubble Space Telescope, they did measure salt coming from an ocean. So this team has measured carbon dioxide, and they have evidence that it is coming from the moon. It's not material that has been delivered by, say, a comet. It is endogenous. At the bottom, I put this as an example of what it entails to actually confirm this measurement. So you have the thin black line is the measurement, and the green line is the sun, essentially. So they are modeling the light of the sun that is reflected by the moon. They're comparing it with what they measure, and they see this excess here, and this is the CO ice. So they confirm it. It's a really good measurement, and that means that it's there, it's present, has been confirmed, and they think it is coming from the moon. So the importance of this is that life as we know it is based on carbon. It has carbon. So measuring CO2 opens questions about, well, could there be some sort of environment that is, friendly to life and all these questions. So confirming this means that we need to go back and get more data and keep on analyzing. But it's really incredible. It is like in our own neighborhood. So planets do form in what we call protoplanetary disks or planet-forming disks. So you have a star, and then you have thick disks with material around. At the bottom, you have a very beautiful depiction of two types of disks. One is compact, and the little box with a black in black with a point in the center, that's actually data, and the depiction is like an artistic rendition. So that's a compact disk. So a disk that is thick and it doesn't have like spaces or rings or anything. You see the difference here between the compact and the large with gaps and rings. So what this team has done is that they took data and they compared the data between the compact and the large disk. And they found that the compact disk has this excess water. It has more water in the inner part than the other disk. So what does this mean? What is this? What is the relevance of this? Well, the importance is that for planet formation, especially for rocky planets, for the presence of life, et cetera, you don't need water and you don't need liquid water. And this team has demonstrated that the presence of a more compact disk facilitates the moving of pieces of ice throughout the disk closer to the star. And closer to the star, it gets warmer, it gets an excess of water, and you have more water available if the disk is compact than if it is large and with gaps. Because when it has gaps, it's really like the ice, the little pebbles of ice that are drifting on the disk, they find like a gap, like a traffic stop. And then the sort of the delivery of this material is not as good as in the other case. So very interesting result because it opens a wealth of new possibilities to understand how the planets are actually formed and how are the conditions for them to be created. This is another, it's a very complicated plot, but essentially every color means that this team has discovered that there is one disk with a protoplanetary disk that has lots of chemical material and chemical abundances. And the importance here is that this is a disk, what we call a highly irradiated disk. So that means that the star delivers lots of radiation. And it wasn't clear if this radiation would actually, prevent from a protoplanetary disk to have things like water and carbon dioxide and many other chemical elements. And it turns out that it doesn't. So you can have a disk highly radiated that still could have the chemical compositions to actually form planets in an efficient way. So what the meaning of this is essentially that you do have more disks where planet formation could occur. We were talking about protoplanetary disks. So you can think of this as thicker and more like the initial phase of how planets form. You have the star, you have the disks, the ices are moving, the elements are sort of mixing with themselves, and at some point they could create planets or not. A debris disk, which is what we're looking at here, is like a later phase where you already have beginning of planets or planets even formed, and you have like debris around that are sort of still, close to the star and the planets. And so this is a very famous one, it's Fomalhaut. And the point of showing this is again to showcase the beautiful details. So to your left, you have a pre-web data of this debris disks, and this is the web data. So there is a new disk that is like a structure that is tilted inside. You see like little rings, you see little blobs. So there is really a lot of additional information that we are learning. The next one is another example of a debris disks, and this is again a very recent result. This is Beta Pictoris, very famous. And I wanted to put this because of two things. First of all, it's beautiful. We're going to talk now about this structure. It's called the cat's tail for obvious reasons. But this showcases a very interesting technique the telescope can do, because at the center of this, there is a bright star. But there is a technique called coronagraphy that essentially simulates an eclipse, like a solar eclipse. So you block the light of the star, which allows you to see much more detail and with much more clarity the disk around, and in this case, a debris disk. So what is this structure here? If you look at it, there are actually two disks. One is the horizontal one, and the other one is like tilted. So the idea here is that the disk that is tilted, it's coming from debris from comets and sort of materials like that. And these two disks had a collision. And in that collision, and we're going to see a little simulation now of that, this structure was created, and all this material is probably coming from here. And these are like, you can think of like residuals on your grill, like, these little black carbonaceous elements. This is what was happening here. And this is a nice simulation or representation of that. So the disk in the bottom is sort of has collided with the one. It has created this sort of tail, and the angle with which we see this tail, it makes it like this beautiful cat's tail. This is the most successful model. When you do astrophysics, you very often have to compare your data with models. And this team, they did have other options, but this was the one that really best fitted the results. So we keep talking about planets, and one thing that WebStat does often is to observe transit in exoplanets. So a transit is a planet that walks across a star. And so in that process, the light from the star is filtered through the atmosphere of the planet. And in that process, you can actually infer what is the composition of that atmosphere. There are two transits, one of the primary, which is when the planet goes in front of the star, and the other is a secondary, which is when it goes behind the star. It's hard to measure. So two big results in here. Webb has made the first detections of key molecules like CO2, carbon dioxide, SO2, methane, SI2, etc. So in the bottom, you do have the black dots are always data. And then all these colorful lines or colorful surfaces, they are models. Because it's really important, you do model the atmosphere. You can, I mean, there are many ways of modeling it. And essentially with a model atmosphere, you compare with your data. And in the atmosphere, you might have carbon dioxide, sulfur dioxide, water, methane, etc. And you always have to compare your results with models and see which one fits better. And this is why often there are results that are not that clear. And this is also why sometimes you cannot really have a strong conclusion unless your data and your models fit really well with each other. We can also talk about rocky exoplanets. And this is a very famous system. It's called the TRAPPIST-1 system. And it's a system that within the orbit of Mercury, at the bottom is a representation of our solar system, within the orbit of Mercury, we have 7 rocky exoplanets. So there's a lot of interest on this system. It has been studied that these are hard measurements, and they're difficult measurements because clouds can contaminate the results, the activity of the star can contaminate the results, and it really needs the highest precision and the highest stability. So it is a work in progress. And so far what we have is that we haven't found any thick carbon dioxide atmosphere on any of these rocky exoplanets, although the effort continues. And here, the points are again measurements, and the rest of the lines are models. And in this case, the models that fit the best are the ones that say, well, we do not have a thick atmosphere in these planets. But again, there are more planets. It's only results for one, and there is a lot of interest on finding and confirming a rocky exoplanet with an atmosphere. And by the way, in case someone is wondering, Webb has not found any solid evidence of life in any exoplanet. Although I know sometimes the press can say that. Okay, so planets orbit around the star. So the stars are incredible gift of nature. The stars are the places where all the chemical elements are formed, the places where your elements that you're formed with from, and everything that's just around us, all these chemical elements come from stars. So Webb is providing new insights on the life cycle of stars. And to keep it simple, we can divide like in two main things. Stars, they begin forming in a star-forming nebula, and we're going to see some images very soon. And we can define, broadly speaking, two types of life. One is a star like the sun. A star like the sun will have, you know, our sun is 5,000 million years old approximately, and it's going to live about the same time. It's like at half of its life. So it's going to have like a quiet life. At some point, it will become a red giant. And finally, it will become a planetary nebula. So it will expand all its outer shells to try and keep the balance and the gravity. And in the end, it will shed all those shells and become a white dwarf. And at the very end, it will just, you know, switch off, so to say. On the other hand, the stars that are very massive, and we're talking about 8 times the sun or 10 times the sun or even more, they live much less time. They, you know, they live fast and they go out with a bang because they, after becoming red supergiants, they become supernova. After the supernova phase, they either become a black hole or a neutron star. So very different paths of life that Webb is exploring. This is our beautiful first-year anniversary image, and it is a star-forming region where you have, give or take, 50 stars similar to our sun in mass, except the one in the center, the one surrounded by all these yellow fluffy structures, that is slightly heavier than the sun. So in this image, the colors are important. The white part of the bottom that looks like a flower to me, these are what we call PAH, essentially organic molecules. They are dust, and it's really glowing because the star in the center is like very young and very bright, and it's illuminating all that structure around. All these red like jets that you can see in many parts of the image, these are baby stars. At the very center, where you don't see anything, like for instance, here, that's a protostar. That's a star being born. It has jets, and those jets are illuminating this hydrogen around it. So these are hydrogen to illuminate jets, essentially. And if you want to look at this in detail, this is from other star, but it's the same thing. At the very center, you do have a baby star being born. It is in the middle of a disk, and these are all the energy illuminating the hydrogen too on the side. So it's really the detail that with which we're seeing this. It's really astonishing, and it's really providing almost on a daily basis new information about star formation and how stars are formed, how they have disks with may or may not have planets, etc., etc. This is a planetary nebula. So this is the destiny of our sun. And this is the same object. It's just looked at it in two different wavelengths, near infrared and mid infrared. Mid infrared is redder, slightly colder element and parts of the object, and the near infrared is slightly warmer. So to the left is the near infrared, and you see here, interestingly enough, you only see a star in the center and all these shells around. So all these shells, again, you see the detail. These are the outer parts of the star atmosphere are being shed, because the life of a star is this constant tension or battle between the gravitational pull and the nuclear reactor that they have in the center. So at some point, this type of stars, they sort of release all these outer shells to sort of release the pressure. If you look at the right, actually, this is not a single star. There are two of them. One of them is shedding all these outer layers, the other is rotating, and they are rotating around each other. And it's this rotation that creates all these filamentary structures and all this like wheel of activity that makes all these beautiful structures in here. So this is not exactly a destiny of our sun, because the sun doesn't have a companion, but it will look very much like this. On the other end, when you have like very massive stars, they end up as supernova. So this is a supernova that exploded many years ago. It was recorded on the 17th century. This is Cassiopeia A, and it is about 11,000 light years away. So again, if you compare the near infrared with the mid infrared, it looks at different parts of it sees different parts and different structures of the same object. So that means that you can understand its chemical composition, you can understand temperatures, and you can really see different layers. Think of this as an onion. Each layer is looked at using different wavelengths. So this is what we're seeing here. And this is the Crab Nebula, another supernova remnant. In this case, it was recorded on the 11th century, and it's about 6.5 light years away. So that means that exploded 6,500 years before the 11th century, and then it traveled, and then it was recorded, and still this is what we see there. So these processes are very slow and incredibly beautiful. In the process of a star exploding as a supernova, what you get is chemical elements, heavier chemical elements that actually deliver all this chemical enrichment to the universe, and we're going to talk a little bit about that later. Stars organize themselves in little neighborhoods that are called galaxies. And again, this is from the release yesterday, a beautiful imagery of a collection of nearby galaxies. They are all face-on. They are individual galaxies where you can clearly see the nucleus, the arms, all these beautiful structures, the clusters, and the star formation going on. So it's really astonishing data that provides a lot of detail. So one thing that there is a lot of interest when you study galaxies. I mean, here, if you look in detail, you see all these bubbles and all these sort of structures like a lace. So all those bubbles are probably coming from supernova explosions that in the process, they sort of, the exact same objects like this, but when they exploded, they create this, they clean up their surroundings. So this is what we're seeing here. These are probably several supernova that exploded and create this sort of incredibly amazing bubbles. And in the process, they may even trigger star formation and create these sort of very complex structures. This is another galaxy, and this is not a JWST image. This is a ground-based image, and this is a beautiful animation. So this galaxy is called WLM. I'm not going to pronounce that because I'm probably going to butcher the pronunciation, but WLM is about 3 million light years away. And if we see this animation, it's going to zoom in, and this is the data that Webb has taken. Well, not yet, but it will appear very soon. There it is. So you see the richness and the very many stars that are there. This is a still image of the same. So this was taken with one of our cameras. And what this team has done is that they have studied in detail the star formation history of the local group of galaxies, of this galaxy in the local group. So this plot to the left, it's a very standard plot that the scientists who study star formation history from galaxies and the stars in general, they always use. It's on the horizontal axis. If you go to the left, the temperature, I don't see it here. I hope you can see it. Oh, sorry. The temperature increases to the left and the brightness increases to the top. So if you look at the bottom left, you will find the hottest stars. And if you look at the right, you will have the colder stars. So each of them, this means that they have studied the star formation history of this galaxy. And if they compare this with models, this is what you find to your right. So essentially, they are doing the number of stars per year. So if you look at this, let's think about this for a second. So what we're seeing here is that on the very first few giga years after the Big Bang, this galaxy did create a lot of stars. And then it went through a very quiet state where it wasn't creating anything. And then it had another burst of star formation, and then it was quiet. And then again. So this is a way of understanding the stellar history of this galaxy. And if you understand the stellar history of one galaxy, then you can actually extrapolate that information into other galaxies. And this was done with a combination of NIRCam data and also HST data. So again, it highlights the incredible power of combining these two observatories. And it highlights each of these points is a star. So imagine, I can't remember how, oh yeah, it's on there. It's more than 500,000 of stars have been used in this study. If we go further away, we know that Webb has found quiescent galaxies at larger distances. And when I say we're talking about galaxies about 1.3 to 7 billion years after the Big Bang, or about 700 million years after the Big Bang. So what is the importance of this? A quiescent galaxy is a galaxy that, like in this case, it goes through a period of, not a lot of star formation. It's really quiet. And the question is why? Why do we have galaxies that are this old, but yet they are sort of taking a break forming stars? So here to the left, this is the galaxy. This is an image, and this is the spectra. And you see all these dips. These are indications of all the stellar population, and these are indications of a galaxy that is really quiet. It's not doing a lot of star forming in this case. And this is a similar thing, just slightly older. So the challenge here is to understand exactly why these galaxies stopped forming a star. Maybe it was feedback from supernova. We don't know. And then at some point it will start creating more stars, maybe because it collides with another galaxy, and in that process it creates more and more stars. So again, food for thought for galaxy evolution. Another groundbreaking discovery with Webb is that it has demonstrated the existence of galaxies about 500 million years after the Big Bang. And this is a big deal because we had never gone that back in time, and we never really had the scientific evidence and the scientific data to prove it. And in this case, we have it, and you can see it here. So to your left, you have a galaxy that lived about 400 million years after the Big Bang. That's an image. And this is the famous Lyman alpha break that we talked about before, that cliff that indicates that this is a galaxy that lived at that part of time, and you can measure this very precisely. If the galaxy, all galaxies have this, so when you can measure it at this level of quality, you're very sure. You need a spectroscopic confirmation of that, and this is what we're seeing here. In this case, this is even an older galaxy. That's why it's, you see how it's fuzzier and a little bit not so clear. This is because it's much fainter, because it's much farther away. This galaxy, we're talking about 320 million years after the Big Bang, so it's really impressive. And galaxies were there, and now we have to figure out exactly how they became to be and how they evolved to what they are now. Not only Webb has found galaxies really at very early ages of the universe, but it has seen that these galaxies are brighter and more numerous than expected. And this image, you don't see it very well because it's very big. But if we zoom in, this is from a collaboration, it's a serious collaboration. And if you look at this in detail, everything that has spikes like this here, this is a star. All the rest, this is a star. All the rest are galaxies. And what we're seeing here is that, well, not all of these galaxies are at 500 million years after the Big Bang, but many of them are. And now the questions are, why are there all these galaxies? Was the star formation more efficient? Is there contribution for population 3 stars? And population 3 stars are stars that we haven't seen them yet. There are some indirect evidence in some cases, but they haven't confirmed. And population 3 stars are the stars that we think were created with a very pristine, very clean initial hydrogen and helium that existed in the universe. So are they there and are they contributing to form these stars? Maybe galaxy feedback, which are processes that regulate the formation and ignition of star formation, for instance, maybe it doesn't work at high redshift as we think it does. Or maybe these galaxies have a lot more massive stars and they can, they are bigger, they are brighter, maybe they are contributing a lot. So these are just potential solutions, we don't know. And this is exactly why this telescope was built, and this is exactly why we made Webb, because we have now new questions and we need to provide answers. And I forgot to say that at the beginning, and I'm sure you know it, but observing these very first galaxies and studying this time of the universe was the first, or let's say the original science case for which Webb was developed. Of course, it can do all the rest and things like exoplanets. It's doing lots of contributions, but this is exactly why this telescope was conceived. Black holes. Again, Webb has found accreting supermassive black holes in the early universe. And this is a depiction that really shows very nicely what we're talking about here. So this is the age of the universe, and 600 million years after the Big Bang, this is perhaps, it's less than 500 million years before the Big Bang, after the Big Bang. And this galaxy has a black hole. So again, how are these black hole creators? We don't know exactly why they are there, how they came to be. You could think that maybe they can come from stellar black hole seeds, that they aggregate with each other, but it really doesn't seem to be a plausible idea. So cosmologists are very excited about these results, and B, trying to figure out what are the mechanisms that made it possible to have these really massive black holes. We're talking millions of solar masses this early in the universe, when the universe was really an infant. Okay, I'm gonna pause this for a second just to tell you this is a fly in one of these very early galaxies. And the beauty of this video is that it's actually based on real data. And its images are two-dimensional. You take an image from a point of the sky and you see all these galaxies, they are not together, not in a space, not in time. So this, I really like this very much because it has taken scientific data associated with where these galaxies were in the universe, and now it's flying through them. And at the end, it will focus on one of these very early galaxies called the Macy galaxy. I mean, look at these incredible structures. As we go farther away, things get a bit more fainter and blobbier, if you want, until you center on this one, which is just a few million years after the Big Bang. And I believe that was my last slide. Yeah.
Thank you. That was so. Oh, go ahead.
No. I'm okay.
Okay, hold on. Let me put a spotlight on you here. All right. Woo! Mind blown. Okay, that was crazy. Thank you, thank you, thank you. And I'm just so amazed. I don't
The
even know
images
how
are,
y'all get.
the data is just so beautiful.
I don't even know how y'all get any work done because you're looking at all the pictures.
It's really distracting.
All right, so it's time for questions and we maybe add some answers. So Richard posted, can James Webb help get better estimates of whether the universe is accelerating or not?
Oh, I forgot about that. I wanted to mention that, and then, I mean, because of time and all that. Great question, love it. So he's talking about the what we call the distant ladder. So we know the universe is expanding, and there is this thing, and so that's measured with the Hubble constant. Essentially, it measures how fast or how slow it is expanding. So if you measure this constant with different methods, interesting enough, you have different results. So if you measure the constant based on what we call the microwave background, like that afterglow from the Big Bang, you get a value. If you measure it with the Hubble Space Telescope some years ago, you got a different value. Now and then there was always the question of, are these results correct? Because you could say, well, maybe Hubble doesn't have enough resolution to actually resolve this data and give you an accurate result. But actually with Webb, the answer is yes. A team, and there are many papers now on that, they have measured with much more accuracy, and they get the same result with Hubble. So the tension is still there. There is an expansion of the universe, it's accelerating, but depending on with the method you use, you get different results. But Webb and Hubble have given consistent results, except that Webb has, it can resolve the stars better that are used for this measurement. And so you get like a narrower error, if you want. But yes, it has been used. You can do these measurements using different methods, and there are different groups using different methods and studying it. But yes, Webb is used for that. It has been already. And we still have questions like, why is this happening? I don't know.
All right, the more we know, the more questions we have.
Exactly.
Richard also follows up with, how do you give the colors to these images since we can't really see in infrared?
Yeah, so that's again a very interesting question, and I think everyone is curious because we keep saying that infrared is a light that you don't see with your eyes, which is true. We don't see it. It's just thermal emission. So the way you do it is that within the infrared you have different colors. Some of them are warmer, like hotter. If it's a hot color, you will give it a blue, like in nature. Hot things are blue. If it is a colder color from a colder temperature, you will give it a red, and everything in between. So our team of experts at Space Telescope, they assign what is called the chromatically, or it's like in nature, warm things, they get blue colors, cold things, they get red colors, everything in between. So they select these filters and they, bring out the beauty of these images. And it makes sense to do it, otherwise we will only have like black and white colors, because what we receive from the telescope is just a bunch of ones and zeros. So you get, when you look at the data, you have like a black and white image that then you have to say, okay, is this coming from a warmer color? Is it coming from a colder color? So you have to assign your blues and your reds for your brain to be able to interpret it. So there is an artistic choice and there is an artistic balance that has to be done. But the reason why when you see a web image, they have this depth is because of that well-chosen palette of colors that is selected.
All right. Claudette asks, when you talk about something being recorded in the 11th century, what do you mean by that?
I mean that there are historical recordings of, I don't know if it was some Arab astronomer that actually did record that star had become much brighter. And so there are historical records saying that a supernova went boom and they saw it. They saw the increase in brightness and that was recorded. That is like a historical record. And please, if I answer any question and you're not happy, ask again because I don't hear you.
Yeah, so, right, so let's see. Oh, lots of questions coming in. Okay, this is good. Has the web imaged any first stars in distant galaxies or signs of it?
I guess you're talking about what we were saying, the population 3 stars, like the very first stars that were born in the universe. So as of now, there has been one group that has, they have the claim that they see in their data in a galaxy named GNZ11, in case you want to find more information. So in GNZ11, the investigator team, they have claimed that they see some emission that could be consistent with population 3 stars, with these very first stars. It's not confirmed yet. I think we need harder evidence, but certainly it's one of the very high profile cases. And the day a team says we have found them and here is the evidence and we are sure, that's going to be incredible.
Jerry asks, might any web observations provide data that could help with the investigation of what dark matter and dark energy are?
Dark matter, because it's dark, web only looks at bright matter, but there are indirect ways of measuring dark matter, and usually it's what we call gravitational lensing. So gravitational lensing was a technique with which originally astronomers defined the dark matter, because imagine, I didn't put any of this again because there is so much data to put, but imagine a cluster, a group of thousands of galaxies that it is very big and has a lot of mass. So if this is the cluster, a light is traveling from a star here. When it gets to the cluster, it sort of wraps around the cluster and then moves. So in that process, the cluster is acting as a natural telescope that amplifies that image, and because the light is wrapping around, you see different mirror images. So the study of that has demonstrated that the amount of mass you need for these mirror images to happen very often is you cannot account it for using only the bright mass, the one we see with like galaxies and stars. So that means that if you sort of estimate your mass and there is not enough by a significant difference, that means that there is something that we're calling dark matter that we don't see, but it is there and it has gravitational properties. When it comes to dark energy, in my opinion, what web can do is just keep on pushing for studying the Hubble constant and the expansion of the universe, and seeing if that fits in the theory. But web is not equipped, if you will, to do dark energy measurements directly. But it can do indirect things like perfecting the estimation of the expansion of the universe.
Well, on that topic, Jillian asks, could the acceleration of the expansion be because galaxies get farther apart from each other and there's less gravitational pull, so they speed up?
To be honest with you, Jillian, no one knows exactly why. I think I have heard a Nobel Prize here in Baltimore saying that, I mean, still it's so many open questions about this. So I wouldn't dare to give an answer with certainty, but certainly it's an amazing topic. We have observational evidence that the expansion of the universe is real. So that's something that is clear. And now the next question is why why are these discrepancies happening and what is exactly going on. So more food for thought. The next generations will figure everything out.
Richard says, remind again, what was the original purpose for James Webb, and what was it designed to see?
Originally, it was so before the Hubble Space Telescope was launched, already astronomers and engineers and everyone, they were like, okay, what's next? And what's next was, we know that, as we talked before, these galaxies that were like the very first galaxies, when they emitted their light in the visible, that light, as it travels to the universe, you have to use the infrared to see them. So that was like the original scientific motivation was like, okay, we know with the Hubble Space Telescope, we can only get to a certain point because of nature itself. You do not see those very first galaxies in the visible, you need the infrared. So the idea was like, let's have a bigger telescope that is only on the infrared and we target that. And then of course you get the bonus of absolutely everything else you can do with it. But that was the original, to observe the very first galaxies and stars.
What I really liked is the whole birth, life, and death of the stars and the materials, and how I'm assuming, and I don't know, all of the materials, since we're all made of star stuff, continues to be recycled.
We are all
throughout.
recycled. Yeah. It's a beautiful, I agree. It's one of the things I find absolutely fascinating. Even, you know, everything we have around, everything we're made of, it comes from stars. And only thinking that through all these, you know, baby stars and disks and complex processes we came to be, it's pretty fantastic.
It's almost as if, I mean, it seems when you compare the images that we've gotten before and the data, that with the James Webb, it's almost like we're looking at the sky for the first time again.
It's true. It's true. If you recall that mosaic with many galaxies that was released yesterday, that team has been studying these galaxies for years. They have data from Hubble, they have data from other observatories, and yet they are like, oh my God, this data with Webb is just fantastic. And again, it's like opening your infrared eyes to a world that I think of it like when you put glasses on and then suddenly you see and everything is sharp. It's kind of like that. Before we didn't have the ability of overcoming the size of the telescope in the infrared and all that, and now we see, and it's beautiful view.
You mentioned in the beginning of the talk about, and I don't know if I caught it, but the mark on the telescope itself, that it had been, is it being dinged by space dust or something?
Yeah.
And was that calculated in as part of the normal wear and tear on the telescope? Are you all nervous, or that there's going to be that that there's too much bombardment
Too much
going
stuff
on?
going on. No, the bombardment going on, it's about, so when we're talking about these particles, they're really tiny. They're super tiny grains of dust. And before launch, we knew this would happen. And the rate expected was about 2.5 hits per month, which is what we're seeing. That particular one that sort of damaged the mirror a little bit, frankly, it was surprising to get it that early, and it hasn't happened ever again. So it's just like a unique event. So that's why I was saying that maybe we were unlucky. Maybe it was just a slightly bigger grain or a slightly faster grain that sort of put a little bit of a dent in the mirror. So what we're doing now to prevent that from happening again is that the telescope is orbiting on the sky on its orbit. And so what we do is that when you observe certain object, you know when it's raining and you're in your car and then you're going against the rain and all the rain is like hitting your windshield, you don't want to do that. So we're not doing that thing of hitting directly with the mirror. So we are really limiting the time that is spent on that region. And being very careful on avoiding that risk. Because at the end, if you get, we get many little hits that are completely harmless and nothing happens, but you want to prevent bigger hits from happening. So we are avoiding the danger zone, if you want.
And Richard asks, what limits or how long will it web stay up there operating? Fingers crossed.
Fingers crossed. So if we talk a bit about historical requirements, so the requirement was 5 years of operations before launch, which is great, but it's just like not enough. Before launch, we knew that there was fuel for at least 10 years. The launch was so much optimized and so well calculated that we saved a lot of fuel. So now we know there's fuel on board for about 20 years. And this fuel is used to, the orbit is a really big orbit and it's a very stable orbit, but once in a while you have to correct and you have to do little corrections and things. That's why you need the fuel. And so fuel-wise, 20 years, of course, there could be wear and tear in other areas, but that's kind of the expectation we have now. So we have web for a long time, hopefully more than 20.
And all of that, the maneuvering and the that's all done from Baltimore. Is that correct?
Yeah, that is correct.
The drivers, whoever drives the
The
machine,
drivers, we have a fantastic flight operations team and engineering team, and they just, they take care of everything.
That's amazing. And then, is it easy to point the web at different? I know that you have to sign up for, if you're a scientist and you're researching, you sign up for a specific time and a place where you want to look, and how has that option been going in terms of operations?
Well, interesting that you asked that, because just this week, the committee that assigns the time slot is meeting, and they are wrapping up this discussion. So the way it works is that typically once a year, we put out a call for proposals, so that inviting all the astronomers to submit their ideas. In the last call, we received 1,900 plus proposals. So it was a world-breaking record. That means that we don't have enough time in a year to do all that. So the ratio is 1 to 9. So every one accepted proposal, there are 9 that are not. So it is high pressure, it is very competitive, and it's all based on scientific merit. And actually, the proposals, the reviewers, and there are different panels like stars and galaxies and planets. And these panels of experts, they review proposals, and they don't know who submitted the proposal. So it's a double-blind process that it helps removing, biases and other things. So it is competitive. It is challenging, and after this week, there will be people who are very happy when they learn. I think the official results will come February, March, around that. And then some people celebrate, some people no, but it's the name of the game. It's a very sought after telescope.
And it's global. I mean, it's not just the U.S. who are using it. Anybody can
Yes.
can submit. Is that correct? There's
That is
a lot
correct.
of cooperation within.
That is correct. We get proposals from all over the world. There are these huge international collaborations that are doing great science with them. So we have a lot of diversity in that area. Yes.
And has there been anything that has been super strange or unexpected that has come up through the first iterations of the imaging?
In terms of the data? I mean, one of the unexpected things is the number of galaxies that are at the early universe, and the number of black holes, and how massive they are. Like, why are they this massive? Why are there so many? Why do we have so many black holes? And that only means that we just, have to go back to the whiteboard or blackboard and start adjusting all the theories and adjusting, because in my mind, there is a lot of interface in astrophysics between data and theory, in the sense that you get your data and then you have to fit the theory around the data. But with Webb, we're looking at a time of the universe that we've never seen before. We have seen older times with things like COBE and WMAP, like the microwave background, and we've seen after with Hubble, for instance. But we have never looked at this part of the universe. So we are learning on a daily basis details about that. If you move closer, again, so many things we don't know about how planets are formed and how they develop. What are the conditions? And we still don't know this. What are the conditions that make a planet a good place for life to develop? So all this, there's also something to say about the very many groups that are working on all these areas. It's not, in my opinion, sometimes you have a single group with a great discovery, but it's usually a cooperative effort where many people put different pieces of the puzzle until you have like a more complete view of everything.
All right. Jillian asked, did I understand correctly? They found some of those galaxies way back are more mature than expected. The earliest galaxies were more mature than expected.
Yeah, so some of them, they have stopped forming stars, which is interesting because in a way, these are not on the first 100 million years after the Big Bang, but after that, there are galaxies that it is surprising that they have stopped forming stars, because in a universe that is this young, I would have expected them to be like actively forming, but something happened that made them stop. And when I say a stop, it's not 100% stop. There is also some star formation going on, but significantly stopping what they were doing and just taking a break. And then maybe they will encounter another galaxy, and maybe that will, again, galaxy interaction, galaxy merging is a process that ignites a star formation. You can imagine all those clouds of dust and material, when they get compressed and hot and sort of changes, that creates new generations of stars. So yeah, in the area of the very early universe, there are many interesting puzzles to solve.
Well, do we have any other questions for Dr. Marin here this evening? You can raise your hand too if you want to speak directly, and you can unmute. All right. Well, thank you so much for this.
Thank you. That was lovely. Thank you so much for your time and for the questions.
Wonderful trip, and through all of the wonderful science that is being done and the great work that y'all are doing. So thank you for all that you're doing, and thank you for sharing with us. Thank you.
Thank you. Really appreciate it. Bye.
Thanks.
All right. Take care, everybody.
Thank you, Shireen. Take care.
Bye-bye.
Bye.
Bye, everybody. Stay well,
Bye.
stay curious, stay outside. Look up at the sky.
Yes.
Go outside and see what's up in the sky tonight. All right. Take care, everybody. Good night.
Bye.